This is the Kaleidoscape, one of the many classes on theater design. This is seating and room acoustics, and Tony Griman is the guest. The reason I'm posting it is because I agree with several of the practices that he's recommending, including doing the Atmos tops, asymmetric acoustical treatments, left wall, right wall. Even the positioning of his 4 top speakers is the same exact position that we have up here. So it's kind of interesting. Here we go.
It's interesting that the topic is seat and acoustics, because interestingly enough, in the chronology of the design of a theater, that is actually where we start. We start with how many seats does a client want? Where do you put them? How do you build an acoustic environment around those seats?
More than 6 seats.
Where do you put the screen relative to those seats so that ultimately the audio and video experience is the way, as we've often said, the way the director intended. So I have about 12 hours of material packed into, 20 minutes? Is that correct? Yeah. So I'm gonna talk fast. The good news is this is being recorded, so you can always go back later and review. But let's do it. So the room size and ratios, well, to an extent, it depends on the available real estate. Nobody ever says, here's a completely blank canvas, you can make a room as big as you want. So often in about 1,000 projects we've done over the last 20-25 years, there usually is an architectural plan that says this is the size of the theater or the media room. To an extent, the client may know that they want 5 seats, 2 seats, 20 seats, 25 seats, so you may actually have to re-influence the real estate allocations on that. Now, figuring out exactly how many seats you can put in the room is way more complicated than architects realize. I often get these plans that show a room that's 20 feet long and it has 5 rows of seats all jammed together with the back row all the way up against the back wall and the front row about 2 feet from the screen. We all know that's not going to work. So I'm going to go into a little bit how you figure that out. Now, what will affect the room size and its ratios are standing wave predictions, but I have to warn you that those are unreliable. So the standard little Excel spreadsheets or little predictors that calculate where all the standing wave ratios are based on the speed of propagation of sound and such really rely on infinitely stiff walls. So I'm going to bring into the screen over here an example of such a calculation. This is actually this is a calculation sheet, and I'm going to show you later some plan sets of a room that we just won one of the best theater awards at the CEDIA for the CEDIA Awards. It was actually just provided during the summer conference in Chicago, the management conference, whatever its name is now. So this calculation of length, width, and heights, standing wave ratios, all is based on infinitely stiff walls, which would be 12 inches of concrete, which rooms we're working in do not have. It's not a bad idea anyway to examine where there will be standing waves and make sure that the length, width, and height ratios are such that there's not multiples. The way we do that over here is we calculate up to the 5th harmonic of the standing wave in the length, in the width, and the height. We created a spreadsheet that sorts those out in a continuous geometric form from low frequency to high frequency, and then compares them. If any of the comparisons shows a coincidence that's closer than 5%, a little warning sign comes up. We can also look at those in a neat little display over here that shows how they're clusters. Ideally, a room that has good sound is one in which the standing waves are evenly spread across frequencies as opposed to all clustered together at one place. And that is all the topic of lots of lectures on acoustics. So I'm going to get that thing back out. So I say that the standing wave predictions are unreliable because for them to really end up being what you're going to calculate, you need to know exactly what the impedance of the walls, what their flexing characteristics are. There's always going to be doors and other elements in the walls. The walls are going to be framed differently from side to side. So in the end, that is not even close to a 60% accuracy. Now, what is important is for the ratio of the length and width to be somewhere around 1.3 to 1.2 to 1.3. This particular room had a length to width ratio of 1.26. So regardless of standing ways, you don't want a room that's too long. I often get plans from architects that have a room that has a room that's 15 feet wide and 45 feet long. You can put lots of rows of seats in there. But in a room like that, the back row is going to be looking at a postage-sized picture, and the front row, if you have lots of rows of seats, is going to be looking at a picture that's enormous. What's better is to have a room that's a little more squarish, not square, but less long, rectangular. That then puts everybody at a more consistent distance to the screen, for one, and for two, also puts you in the middle of a circle of speakers that's more consistent all the way around. Now, in the room size and ratios, you want to make sure that you have a height that's sufficient for the riser platforms. After you decide how big the screen is, you got to be able to set platforms for sidelines that are tall enough that everybody can see over everybody else's head, and that there's still room for ceiling treatments and ventilation and lights and the top speakers in the wonderful world of immersive audio for Atmos. So I'm going to pull up right now the plan set for that particular project, the one that won in, I think, Best Theater Level 3, if I remember right. And this actually shows, let me see if I can go to the full screen mode. There we go. I hope you guys can all see this. Andre, if you're still there, can you confirm with a verbal thumbs up that you can see this diagram on the screen?
Yes, I can.
Hallelujah. All right, so this is the particular room that won. Not a very long room, a comfortable room. And you can see the sightline study over here. It was actually compromised by the entrance area of the door, which I'll show you later. So there's a very slight overlap over here that was known. The client accepted it. They knew what it was. But we needed to have enough ceiling height to be able to put the projector and the screen and the speakers and make all that work, and also so that there's sufficient headroom all the way at the back without feeling like you're in a room that's got 6-foot headroom. So you need to consider all of that. Now, my favorite way to design a room is to have it be an open pit, which is a big rectangle where the entrance door is at the back, and until you build the riser platforms in it, it is a thing you would fall into. And that is so that you can build the riser out of typical wood or metal framing later on, after the concrete's all poured, if it's a concrete space, and so that you can, under that riser, run HVAC and use it for base absorption. We have a client right now who's building a big room. They're going to have some storage under there. The stairs are actually going to lift up, and you can push some chairs and stuff in there. So again, my favorite way to start this whole thing, go back to this diagram, as you can see from here, when I move that over there, please give me a second, dink, click. You're not seeing where the entrance room is from this diagram. Let me go to the entrance door. So I'll have to go way further down to show you that. This is a view, this is a section view from the left, looking with the left wall behind you, looking at the right wall. That's the entrance door of the room. You enter into this room at a height that's about 12 to 14 inches above the actual bottom of the tub, and the platforms are built inside there. And that just makes the ergonomics of the room work way better. We're often given startup designs by architects in which a riser has been poured out of concrete, and that's a bit of a disaster for lots of reasons I'll be going into. All right, so at this point you have, let me recap over here. You've looked at the design of the room, and you've worked with the architect, with the builder, whoever you're working with, to figure out what the length, width, and height need to be, and you've put in there some level of assurance that the seats can fit, and we'll talk about that in a second. You've made sure that the room is not too long, and that there's room for risers and the ceiling treatments and everything in terms of the height and the width, etc. So next up, we're going to set the placement for the audio and video. Let me actually go back a little bit on this. About the placement of seats, I know I'm going to repeat this a little bit later, but I want to bring up an Excel spreadsheet here again. spreadsheet. It's a proprietary thing we built over the last 20 years. So we have looked at the length, width, and height of the room, and then based on that, we've brought that directly into the spreadsheet that looks at where the seats should be relative to standing waves. I'll get back to that a little later. But it also auto-calculates based on the size of the seats that we can put in over here, the actual dimensions of the seats. It auto-calculates how many seats we can put in. I'll show you that really quickly. So we actually tell the program we want the seat ear height to be over here. We know that we want a screen that's a certain dimension in order to give us the right size of the screen. I'll get to that in a second. This particular program is going to automatically tell us what the riser heights needs to be to have the proper sight lines through this thing called Victorial Math. It's going to tell us where the speaker locations need to be, and it'll predict based on the seat sizes, in this case 22-inch seats with seats that have 22-inch pads and 6-inch arms. It predicts that you can put 5.4 seats across with 36-inch aisles on either side and a stretch fabric boundary and the walls and all of that. You need to know that as soon as possible in the process. A lot of people wait till later to figure that out, and then you get painted into a corner. So, seat placements for best audio and video. Again, available real estate. How many seats can you put in this room? I've just shown you that we figured out you can put 5.4 in that particular room. Now, where do you put the seats? So you guys have all heard of standing waves, and a funny question I often ask is, if there's a standing wave when you stand in a room and you sit down, does the standing wave go away? And the answer is, well, it depends on what's a vertical or a lengthwise or a widthwise. But when we're doing our calculations, we try to put seats at what we call the magic ratios, which on this spreadsheet, I'll expand over here, are these ratios of the length of the room. If you put a row of seats at 0.8 of the length of the room, or 0.68 of the length of the room, or 0.55, 0.45, or 0.32, while you will not get rid of standing waves, you will be in a place where you won't hear severe peaks or dips of the standing waves. I mentioned that finding out exactly the frequency of the standing waves is a little bit unreliable. That is true. But regardless of the frequency, the dips will typically be at a half and a quarter and other well-known peak and dip positions. And as long as you seat at these locations, you put your rows at these locations, there's a fairly good chance that you won't be subjected to cancellations or big peaks in the sound. So we look for what those are. The program here predicts that, given the size of this room, there's an option to seat people at 18 feet from the front wall, 15.4, 12.47, 10, and 7.25. Obviously, 7 feet from the screen, or 7 feet from the front wall, in which there's going to be, in the case of this room, an acoustically transparent screen and speakers hiding behind that, it's going to be a little too close. We're not going to put anybody that close. But in this particular room, we chose to put a row of seats at 18 feet from the front wall at 15 and 9.4. What that looks like in the locations, I'm going to go back to the start of our plan set for this. By the way, the judges for the CEDIA Awards are very excited about looking at documentation like this that shows that good homework has been done. That's one way to win an award, is build a good room, but also have really good documentation. So the location of this row of seats, that row of seats, and in the case of this room, this bar row that's at the back, is based on these ratios I showed you earlier. This particular length over here is the 0.8 of the length of the room. This is the 0.68, and that's the 0.45, if I remember correctly. 9.4, 15.1. So this one actually, we did a 15.41 location and then a compromised front row, knowing that there was no other way to do that. So this is the point in the presentation where I go, you're going to do a lot of math, a lot of predictions, and then you're going to have to accept compromises because there's times where it doesn't all fit. And to me, the best engineering of a room is one in which you apply the best compromises. You carefully choose what's going to screw up the result the least. All right, so here's a row of seats, here's another row of seats, here's another row of seats. If you could actually overlay where there's going to be peaks and dips and standing waves, you'll find that there's not going to either be dips here, 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 or peaks here, 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 and you end up with a good chance that the sound will be decent as far as the length standing waves. The width standing waves, you want to do the same kind of thing, and this shows where the seats are located, and as much as possible we try to put those main seats at places where there's not strong standing waves. There is a row of seats in the middle of the room, and there will be dips in the standing wave over here from the left to right standing waves, and the way we're going to solve that is by putting 4 subwoofers in the room and tuning them to move those dips or cancel out those dips. We'll talk about that a little later. Back to this. I guess I have to hide that. I got to go back over here. All right. So the seats are placed relative to standing wave predictions. They're also placed so that there's sufficient spacing for comfort in recliners. If somebody says, I want a full recline, you need to have the spacing between the seats at 72 inches or more. Otherwise, the feet of one row are going to be in the head of the row in front. And if they say it is sufficient to just incline a little bit, you maybe don't need as much of a spacing between the seats. Next up, on placing your seats, and I touched on this a little bit, you got to make sure that the heights of the seats provide proper sight lines. And that's done by either doing a graphic layout in the room, by just drawing the thing up, or by doing the math like I showed you on our spreadsheet. Now, make sure that you're not putting the front row too close to the screen. Even with ultra high definition and with a really good projector, you don't want to subject people to watching a screen that subtends at any bigger angle than 70 degrees. That's a huge picture. Ideally, the target of the sight line is, the target subtended angle is about 45 to 50 degrees. And if you watch a screen as big as 70 degrees, which is, if you can imagine, it's just enormous, you're going to end up with nausea. You're going to end up seeing, you may see grain in the film if it was shot on film. You'll see pixels. You'll see problems. So don't get people that close to the room. Now, in selecting the screens, by the way, do pay attention to what I call butt hours. There are seats out there in the market that are designed to hold you comfortably for 2 or 3 hours, and others that cost a little less money that after about an hour of sitting, you'll actually find yourself squiggling and moving around because your back hurts. And seats are actually rated in the seat industry as in butt hours. It's a funny thing. All right. If a client says, I want to be able to recline all the way back, you need to educate them that that's not really an ideal way to watch a movie, because then you've got your head cocked all the way forward. It's comfortable for sleeping, but not very comfortable for watching a movie. Ideally, you just want to recline a bit and not go all the way back. Now, the main thing you want to be trying to do is to cluster those seats as close together to each other so that there's performance consistency. If there's a huge distance between the front and back row or the left and right seats, there's going to be big variations in the picture and sound performance. So as much as possible, try to get these things as close as possible to each other, which means avoiding full recline, which separates the rows by 6 feet. If the client says, look, I want a room where there's a lot of spaciousness, a lot of distance between the rows. It's really important to me. I want the sense of comfort. Well, that's the client specification, and you may have to go for that. But ideally, you want to cluster these seats as close as possible to each other. All right. Next thing is deciding the screen size. I know that was part of another module, but in our design, the screen size is an integral actually into the acoustic design of the room, because it's going to dictate where speakers may or may not go, what the riser heights are, and lots of different things. I want to remind you that ideally the width of the screen is such that it subtends 50 degrees of horizontal angle. That means that if you draw a line between the left of the screen and your head, and then another line to the right of the screen, that angle forms 50 degrees. I don't talk in screen heights anymore. It's just really confusing. I don't talk in screen widths and this stuff. I just talk in degrees. It's a lot easier. Now, you can do the vector math for that, or you can just know that if you plan on a screen that's 0.93 times the main seating distance, that's the correct size of the screen. So if you're sitting 10 feet away from the screen should be 9.3 feet wide. Whether it's a 178 or 235, 236, 237, doesn't really matter. Now that number comes from both the target of what the filmmaker is intended for 4,000 pixel displays to present resolution for a human being who has the ability to see as small as 1 minute of arc, 1/60th of a degree if a human has 20/20 vision. Now,
that's the screen width, right?
That's the screen width, not diagonal. Please, anybody who's listening, looks like there's 18 people, stop talking about diagonals. No more diagonals. Why? That was invented by the TV industry to make screens seem bigger than they really are. It's extremely confusing. It doesn't tell you much of anything. Talk in screen widths. That's what matters. All right. In terms of where the screen goes, ideally, the main seat, sometimes known as the captain's seat, the money seat, the screen should be placed so that that person is looking at 0 degrees to the middle of the screen. That's ideal. That's what's comfortable. But if you design rooms like that, you may not actually end up with proper sightlines. So you may need to raise the screen up. If you raise the screen up from that, please be careful not to put the front row of seats, let me go to that, any higher than 15 degrees. Hey, look at that. On this project that won for Best Theater, we actually had to put the front row at 16 degrees. So that is off by 1 degree, I think, between us. Like I say, good enough for government work. I see rooms in which the front row is looking up at 20 or 25 degrees, and it's extremely uncomfortable. It's an unpleasant way to look at a movie. This row over here, the main row, is looking up about 5 degrees at the middle of the screen. That's perfectly comfortable. All right. Now, do you choose a 1.78 or a 2.37 or 2.35 aspect ratio? Notice I didn't say 16:9. I don't know who came up with. Notice I didn't say 16:9. I don't know who came up with the idea of a funny thing to divide. I like to talk in screen size, screen ratios that are 133, 178, 235, 237. Those things are what our clients can understand. Which one do you pick? Well, it depends on the use cases of the client. If the client's going to watch a lot of sports, you may want to stick to a 178 screen. If they're watching a lot of movies, you may want to do a 235 or 237 or 239 aspect ratio. Some of it depends on the ceiling height. If there's not a lot of room to the ceiling, you may actually need intentionally to scrunch down the height of the screen to 237. And if you're doing that, you may want to introduce masking and zooming to the projection in the screen system so that you can convert from one to the other. Now, reason I wanted to talk about all this is that is part of the design acoustically of the room. Please, please, please always use an acoustically transparent screen. Woven materials are best. They're essentially like grilled cloth. They barely affect the sound today. And that allows you to put the speakers, all 3 front speakers, behind the screen. So make sure you have enough space for those speakers and add about 3 inches of clearance when you're doing a woven
wall screen can sound better.
If it's a micro-perforated screen, you're going to need 6 or 8 inches of clearance to avoid any high-frequency bounces off the screen. Now, next thing in the process, in the order of this design, is the riser heights. Now, I showed you earlier in our spreadsheet that we calculate all of that in one go, but the order of calculation is how many seats can you put in the screen? Where are you going to put them relative to the length of the room? How big is the screen? Now let's figure out the sidelines. I generally like to add 2 to 4 inches above the heads of the person in front to make sure that there's comfort and that there's good tolerance. If I'm sitting on the back row of the room and I'm really short, I'm only 4 feet tall, and Andre Floyd, who's 7 feet tall, sits in front of me, the sidelines are not going to work out, right? Those numbers, by the way, were fake news. I think I'm a little taller than 4, and I don't know that Andre is as tall as 7 feet, but you get my drift. Now, in designing the height of the risers, so I'm going to go back again to our spreadsheet. So again, the way we do it is we don't start with it graphically. We actually do it by deciding where the rows are going to be. We decide what the height of the seating ear heights are. We decide how far up, how many degrees we're going to tolerate the front row. And the spreadsheet actually tells us automatically what the riser steps need to be. All right. So in this room, we need a 16-inch riser step. We didn't get that because the concrete tub was already built. I think we only got 12 inches. But when you decide the sidelines and the riser, pay attention to the stairs and try to make the height of the riser something that's an integral multiplier of steps, and steps want to be between 6 and 7 inches for good comfort. So try to go in even chunks of that. Next, you figure out where the platform depths are, like where actually are the steps of the platform, like how far they are from the back wall, and that's defined by a number of different factors, including the size of the seats and whether if they are recliners or incliners. Does the back actually need room to scooch back? And if so, you need to provide a gap. If there's a gap between the front face of the riser and the chair, and that gap is 6 inches, beware, that's somewhere where somebody, if they're walking around in the dark, could actually put their foot and twist it. So you got to be a little careful with that. Also, when deciding how tall the riser is, make sure there's sufficient headroom at the back of the room. I've seen designs where there's only 6.5 feet of headroom at the back, and you're going to bonk your head on the projector or obscure the projector beam if you're standing up. So you got to pay attention to that. Now, the reason I like to build risers out of wood or metal framing after the pit is done is you can hide ventilation return ducts in there, and you can hide base absorption in there. You can actually perforate sections of the top of the riser, fill the riser with insulation or several layers of R30, and now you got yourself a nice big base absorber. I also like the riser to be resilient, as in to bounce a little bit. So my favorite way to do it is to have it made out of wood, sitting on actual rubber pads, or sitting on a subfloor that's mounted on top of a rubber mat. And that gives what's called haptic effects. You actually feel the vibration coming up the riser into your back, and that gives you better bass perception and puts smiles on the clients' faces when they feel the bass instead of just hearing it. All right, I'm going to quickly go through the speaker locations and treatment locations and actually stop talking. So, high points. Left, center, and right speakers should form a 45-degree subtended angle to your the main seating location, and they should be behind an acoustically transparent screen. They should be all the same type and at the same height. I keep seeing these designs where there's a pair of vertical left and rights and a horizontal center all behind a screen. It's like, no, no, no. The horizontal center speaker is a compromised design that's meant to go below or above a screen. If you're using an acoustically transparent screen, it should be the same 3 speakers. In terms of height, those speakers should be somewhere around the mid-height of the screen, but if they're vertically directional, you're going to have to be careful in their directional beam. For good audiophile performance, you would want the tweeters and mid-ranges to be somewhere around 6 inches above seated ear height, which may not match the mid-height of the screen. So you have an and/or condition, and you need to figure out the use case with the client to figure out whether they're going to be mainly listening to music in this room or mainly doing movie screening, and then decide how high up the screen you're putting this. You do want to put the speakers at a height, also in a width, to try to avoid cancellations from either reflections in the room, what's called a speaker boundary interference response, or where there are standing waves, and our spreadsheet shows some calculation predictions on that. Here, just for giggles, I'll show you that because it's kind of interesting. So yeah, there's a bunch of numbers in here. This is complicated stuff, lots and lots of values. There's a bunch of charts over here that we calculate for the different speakers at different locations. You need to be doing that. You don't want to put a speaker at a location where at the main seat there's a giant hole in the bass at 180 hertz. That's going to sound bad. So, all right. Side speakers should typically be at about 100 to 110 degrees relative to front center. You may need 2 sets of side speakers. They should be up 15 degrees from seated ear height. I am tired of hearing people saying that, oh, in immersive audio they should be at seated ear height, or for listening to music they should be at seated ear height. Lots of research has shown that that's wrong. Up 15 degrees is right, which is typically about 24 inches above seated ear height. And
that's
then they should be aimed to the seated ear.
No more than 1 foot. Tony's wrong there.
Speakers should actually be pretty tight to each other, 160 to 170 degrees from front center. If you space them out too much, you won't get a sensation of back sound. Instead, it'll be a sensation of spaciousness, which is not what you want from the back speakers. For immersive audio, the wide channel speakers, those are the ones that are halfway between the front channels and the surround channels, which I'll show you over here on this diagram. These are the two sets of side speakers. These are the wide channel speakers. Those should be somewhere. Here, let me show you the top view of this room. That's the wide channel speaker. That's 0 degree. That's 22 degrees. Left speaker.
Real 4.
That's about 90 degrees to the wall. That should be at about 45 to 50 degrees. And that channel adds really good sound quality and resolution in the spatial domain to the sound. You should put them in there. And then finally, the top speakers should be on two lines that are at a midpoint between the left and center and the center and
you
right.
see, that's Atmos spacing.
Here again, I'm going to go back to the diagram to show you what we did on this room. And
Cinema Atmos spacing.
I'm going to need to go down here. I am conscious that we're way out of time, so I'll finish this up. This is a reflected ceiling plan of the room. This actually shows a peel-out view of the speaker locations and acoustical treatments. This is a reflected ceiling plan. That's the left wall, right wall, front wall, and back wall. Here's a reflected ceiling plan, and that shows where we put the top speakers. So the seats are over here. The left and right speakers are here, center speakers here. This is a midpoint row and a midpoint row for the top speakers. Don't put them too far away or else you're going to confuse the top sound for the side sound.
Like I've been saying for, what, 5 years
now? Resolution in that direction. You really want them here. That's also how filmmakers are listening to the move to the top speakers when they're in the mix rooms. Andre, we're still okay, or are we losing audience here?
Oh, we are still good.
Okay. We're supposed to end this at 10:30, correct?
We hadn't lost anybody. I think this is great information, so I'm sure everybody is excited to hear more.
All right, you guys, thanks for hanging with us. Of course, I will be at CEDIA. I am teaching a class. We have 2 classes there in which we're going to address some of this stuff. So if you want more of this, please feel free to come to those classes. All right. Now, finally, acoustical treatments. So that was supposed to be just a simple topic of today's presentation. There's a lot that leads into that, but let's go over that. So for good sound, you cannot have a room that's all reflected surfaces. It will not sound good. I don't care what speakers you're putting in there. You need to treat that. You need to damp down those sound reflections, but not too much. If you overdamp the room, it's going to sound bad. Believe it or not, the target is about 15, at most 20%, but typically 15% of the surface is covered with absorption. So if you look at your front wall, your right wall, your left wall, your back wall, your ceiling, really only 15% of that surface should be absorptive panels or materials. They should be evenly distributed around the room. Don't cluster them all in one place. And ideally, I like modules that are 24 by 48 inch panels, a minimum of 2 inches thick, preferably 4 to 6 inches thick, so that they treat a broad range of frequencies. So don't overabsorb, just 15% is all it takes. Now, in addition to absorption, to damp down the reflections, it's good to scatter some of the remaining reflections by adding another 15 to 20% of scattering surfaces. Those are modules that are known as diffusers in the market, scattering panels, whatever. People have all kinds of different names. And there's a thing I call a 2D diffuser and a thing I call a 3D diffuser. I am not using the math in the description of the quadratic equation dimension. I'm talking about how the sound that hits the diffuser is scattered back out, either in 2 dimensions, as a hemi-disc, so as a plane, or as a hemisphere, which is in 3 dimensions. I like to put 2D diffusers on the sidewalls towards the front of the room and 3D diffusers towards the back of the room. And I like to interleave those things with the absorbers. Again, minimum of 2 inches thick, preferably 4, 6, 8, even 12 inches thick. Let me go back to the diagrams on this to show you on this room. Again, it was good enough to, one, sound really good, but also win a CEDIA award for good design work. So I guess we're not the only ones who think this is the right way to do it. So this is the left wall of the room. Look at the layout over here. So the front speakers are here. Excuse me. Screen is right here. Floyd, when I move my my mouse wand over here, do you see me moving that up and down?
Yes, I do.
Excellent. So screen is over here. Speakers are over here. In this particular room on the left wall, first thing is a row of 2D diffusers. They're sort of like a part of a cylinder that's on the wall, a row of 3 of them. Then we have
You see?
absorber panels.
This is what I'm doing.
Inside of which is inserted the left wide speaker, what I call WL, wide left. Then there's a row of 2D diffusers. Then we have a surround speaker and an absorber above and below it. Then there's a row of 3D diffusers. The sound that's going to hit this is going to scatter back out.
By the way, don't use small speakers like those are ridiculously small. You need full bandwidth. Remember that.
Then there's some absorbers, a bit of 3D diffusers, and then there's a door here to the machine room which is covered with an absorber. So that is the left wall. Let me go to the right wall, and you'll see some of the same. First off, from the front wall is some absorbers. Then there's a row of 2D diffusers, row of absorbers, row of 2D diffusers, a door to get in the room, a row of 3D diffusers, and then an absorber. Those of you who have a keen eye will notice there's an asymmetry between the left and right walls. And yes, that is intentional. Let me actually go to the peel-out view, and you'll see that.
I've been saying that for 5 years.
We found a long time ago that doing an asymmetrical layout of the absorbers and the diffusers, as counterintuitive as that seems, actually ends up giving you a better sound field. There's actually been some research on psychoacoustics that show that scrambling the correlation of reflection off the left and right wall helps your ear brain system determine where the sound's really supposed to come from. I won't go too far on that. It has to do with intraoral cross-correlation of the sounds. I love throwing in big words in there that confuse people. But it makes me sound smart. See, that's all it takes. So the left and right walls, some absorption, not too much, some diffusion, asymmetrical layout, interleaved between absorption and diffusion. Let's look at the back wall. There's the back wall. Middle of the back wall is treated with absorption in order to reduce the amount of energy that's going front to back in the room in that sound field, which would otherwise narrow up the sound field. And the outer parts of the wall are treated with 3D diffusion. Some panels here, some panels there. We have another door here to a mechanical space that ended up getting covered with an absorber. If there's room, I like to put diffusers on those, but there was no room in this one. So that's a typical layout for the left, right, and back walls. Ceiling is treated this way. A cluster of absorbers towards the front of the room and a cluster of 3D diffusers towards the back of the room works really, really well. On larger rooms, we'll interleave some absorbers in the middle of the ceiling. All of this stuff is 2, 3, 4 inches thick. 1 inch doesn't work. Don't use that. But starting at 2 inches for absorbers and 3 or 4 inches for diffusers, you get a good effect. Finally, the front wall is pretty simple. There's some absorption on the baffle walls that we put the speakers on, and then some low-frequency absorbers, which are tympanic membranes all around the front wall, around that, to get rid of low-frequency character. I sometimes see people put diffusers on here, and that's completely pointless. The energy that's coming out of the speakers, the mid and highs, is all coming towards you and not going back to the front wall. So there's no point in putting diffusers over there. Looks pretty maybe on pictures, but doesn't help sonically. All right. You also want to put some base absorption and trapping in the room. We do that by using the riser and some tympanic membranes here and there, and there's the simple diagrams you saw. Now, all of this stuff on the wall is ugly, and you want to cover it with acoustically transparent fabric. That's the way it should be done. If you look at the CEDIA website, you'll actually see how we did that. I'm out of time, so I won't show you that. But the room doesn't show any of these treatments with speakers. It's all acoustically transparent fabric. And how much does all this stuff cost? Well, count on at least 10% of the audio budget for a 50% improvement in the sound quality. The difference between a room that's untreated and a room that is treated is about, it doubles the perceived sound quality for just an extra 10% of the budget. It's well worth it. Okay, I had some stuff on ventilation and low noise. The room needs to be quiet. That's what I'm going to say. It's a complicated thing to design a ventilation system that's quiet. You ultimately want what's called NC20, which is a perceived 20 decibel background noise, and you got to do a whole bunch of things to get there. A good ventilation engineer will do that. A good acoustical engineer will know how to do that. And then you also want a room that is isolated from its perimeter so that it gets an NC20 target. If there's a bunch of noise outside, it's going to get in the room, it's going to disturb you. But also a good theater working correctly is going to put up put out up to 120 decibels of sound, and it's going to be very annoying to everybody around the residence. So you want walls that provide more than 60 decibels of sound isolation, which is also known as STC65, sound transmission class. And that takes special walls that are floated, that are resilient. You have to have enough mass. You have to have damp structures. You have to have sound rated doors. The devil's in the